So we still need to graph tangents and cotangents. So I am going to do F first, where I am going to graph -2 tangent of 5x. Now remember, our tangent functions look like a normal cubic unless they've been flipped between vertical asymptotes. Our cotangent looks like that, kind of a flipped cubic. Let's take a look at what we should see for F. Now, a tangent graph normally goes between 0 and pi, remember, because of the fact that it is going to have a period of pi before it repeats. And then if we cut that in half, that's pi over 2. And then here we have pi over 4 and 3 pi over 4. Okay, so it actually counts by pi over 4s, 1/4, 2/4, 3/4, 4/4. Okay. The way that a tangent works, remember tangent's y over x. So it's at 0. There is, this is 1. This is a vertical asymptote because that's undefined. This is -1 and this is 0. So that's the chart you can memorize for your tangent. Now, let's take a look at all the things we know about this particular function. There is an amplitude or a stretch of that -2 in front. So what does that -2 do? Well, that -2 is going to flip it, and it is going to make it stretched by a factor of 2. That is going to affect your y values. Now, that's the only thing on the outside of the function, so that's the only thing that's going to affect our y values. So we can look at our y values right now. If we go ahead and multiply all the y values by -2, we get 0, -2, a vertical asymptote, +2, and 0. So that outside stuff always affects your y values. Now the inside stuff is going to affect our x values. So if we set 5x equal to pi, that's going to tell us what's going to happen to our period. You'll notice we have to divide by 5. We have to divide by 5. So that tells us that every one of our x's need divided by 5s, unfortunately. So if I divide these by 5, I get 0. I get pi over 20. I get pi over 10. I get 3 pi over 20. And I get pi over 5. So this has a very, very fast, quick period about it. It always finishes one cycle at a pi over 5. You'll notice that our highest denominator is 20. So when we go to set up our graph paper for this one, I am going to have to count kind of by 20s, but just go 1/20, 2, 3, 4. And we only have to go up to pi over 5, which is 4/20. So let's put that there. Okay. Now let's count the same way in the opposite direction. Okay. Now, always just like a secant and a cosecant, the first thing we want to put on our graph paper is our vertical asymptote. We have, and I'm going to count by 2s, guys. We have a vertical asymptote at 2/10 or 2/20, I'm sorry, which is right here. So now we know that we should have another one. Okay, let me put on the rest of the graph because this tangent and cotangents are the hardest, and that's why I kind of did this last. At 0, we're at 0. At pi over 20, we're down at 2. That gives you half of my cubic. So the other half of my cubic goes up this way. So this is where our vertical asymptote goes. Do you see that? So let's put in 2 more marks here and 2 more marks here. Okay, So this would be center, up, down, vertical asymptote. Center, up, 2, down, 2, vertical asymptote. So again, those are probably your hardest. And I am not going to give you any that count. The grossest I'll have you count is like maybe by pi over 4s. Counting by pi over 5s is pretty nasty. So that is not something I plan on doing for you. So that is your tangent graph. So now let's look at a cotangent. So we have a stretch of 2. So just like our tangent had a 2 stretch, this one's going to have a 2 stretch, but this one hasn't been flipped over. So it's still going to look like this. Okay. Let's take a look at how it has shifted. If we set that equal to 0, that's not only going to be our starting value, but that's also going to be our phase shift. So that's our phase shift and our start. So if we set that equal to pi, that's our ending. So we would get pi over 2 as our ending. And then if we set just x equal to pi, that is our period. Okay. So let me give you the chart for a cotangent. Cotangent starts at 0, ends at pi. That's one cycle of it. So just cut that in half and cut that in half again. Now remember that the tangent was y over x. The cotangent is x over y. So if we go around the unit circle and we do x over y, the first thing we get is 1 over 0. So that's a vertical asymptote. And then we get 1, and then we get 0, and then we get -1, and then we get a vertical asymptote again. So tangent is the hardest. It is the hardest graph to wrap your head around. Cotangent, it starts at a vertical asymptote, ends at a vertical asymptote. You'll get the little swoosh in the middle. It's perfect. It's wonderful. And then you can space it out from there. So I really like cotangent graphing much better than tangent. Tangent's just kind of icky. Okay. So now let's go from here. The 2 is going to stretch it. It's only going to affect our y's. So let's multiply all of our y's by 2. We get a vertical asymptote, 2, 0, -2, vertical asymptote. So that's what the 2 does. It just affects our y's and only our y's. The x plus pi over 2 affected our x's. It starts where that parenthesis equals 0. So it's going to start at -pi over 2. And then it's going to end where that parenthesis equals pi, which is positive pi over 2. Now that's a good way to count. That's not hard to do because right smack dab in the middle of negative pi over 2 and positive pi over 2 is 0. So that's good. And then halfway between a half and 0 is a fourth. So this is negative pi over 4 and positive pi over 4. So that one wasn't too bad to figure out what the chart is going to be. So my x-axis, I am going to need to count by pi over 2's, no, pi over 4's. So I just broke it down into fourths. I have to go up 2 and down 2. So that's what I'll put on there for my x-axis. Now again, you could count a little differently, and that's okay. First thing we always put on for all of these graphs that have vertical asymptotes are the vertical asymptotes. So at negative pi over 2 we have one. At positive pi over 2 we have one. Now do you see how that is 1, 2, 3, 4 spaces? So we can count 4 spaces. It's not a bad idea to put those things on so we have some full cycles of our graph. So if we count 4 spaces to the left and right of there, then we also find more vertical asymptotes. Now let's put on our swooshes. So at 0, we're at 0. At negative pi over 4, we're up 2. At positive pi over 4, we're down 2. So our swoosh, our cubic sort of looking thing, it looks like that. And then we can do that. Smack dab in the middle, you're always on the midline. This one goes up to the left and down to the right. Put in your cubic-like thing. Smack dab in the middle of your vertical asymptotes is always the center. This one goes up to and down to. There were no flips. That is just what a cotangent looks like. So that is our graphing. That is the graphing. You have lots of resources you can use to get yourself ready for this. CCP students, make sure you know how to do this by hand. If you're not a CCP student, feel free to use the resources that are out there, but you are going to have to show your work. Okay? So those are our graphs. Now let's go back up, and we left off now with number 14. Now you'll notice on the side of the page right here, it just says that for a cosine, you only have to look at values between 0 and pi. For a sine, we only have to look at values between negative pi over 2 and pi over 2. For an inverse tangent, we only have to look at values between negative pi over 2 and positive pi over 2. That's what the pictures are on the board. So that's just telling you where you get to look on your unit circle. You only have to look at 2 quadrants for our answer. So if we look at 14a, it is saying, where is the cosine square root of 3 over 2 between 0 and pi? Well, it's positive in the first quadrant, so our answer would be something from the first quadrant where the cosine is square root of 3 over 2. So you have to see how it says to use or evaluate the expression without a calculator. That's because we're going to use our unit circle. And so the angle measure that does that, I want in radians. The angle measure between 0 and pi over 2, where the cosine is square root of 3 over 2, is pi over 6. So it's just knowing your unit circle. B, what angle measure gives us a sine value of negative square root of 2 over 2? We're going positives, we're using the first quadrant. Negatives, we're using the fourth quadrant as our negative. And so this is negative pi over 4. Now, let me show you what I do for a tangent, and hopefully this will help you. If I see radical 3, if I see radical 3, positive or negative, first thing I always do is put it over 1. Next thing I always do is I cheat a little bit, and I think, okay, there had to have been a 2 there that they canceled out, just because I know what values are on our unit circle. So technically, a negative 3 for a negative radical 3 for a tangent is really when our y value is negative radical 3 over 2 and our x value is 1/2. Okay? That's the easiest way to think about that and break that apart. So the tangent, like the sine, we are just going to look for values between positive pi over 2 and negative pi over 2. That's negative. We know it's the fourth quadrant. No, I'm sorry. Well, it is the fourth quadrant, but in the negative version. And so that is going to be pi over 3, 60 degrees. And since it's going down, make it negative. So that's a little bit of that. That is 14. Just going backwards on our unit circle. What angle measure does that? Remember, this notation means what is your angle measure? Now, although I didn't circle it, could we please at this time, we're going to do number 16. Please, we're going to do number 16. Remember, if I skip it, you skip it. Down at the bottom of your page, there are some pages in yellow. That is me doing the problem step by step, and that's a good resource to use as a study guide when you're studying for the test. Okay, anyway, let's take a look at 16. It says the sun is 25 degrees above the horizon. So we're going to make a little picture. So our angle of elevation is 25 degrees. It says find the length of the shadow if a 100-foot building casts that shadow. Round to the nearest hundredth. Okay? So that's the picture that goes with number 16. And once we have a right triangle, because we're assuming that building is straight up and down from the ground, let's go ahead and label what our sides are. I tell you every time when we are setting up a picture that ends up being a right triangle, always label your sides. So this is our opposite, this is our adjacent. So then you ask yourself from SOHCAHTOA, what uses opposite and adjacent? Well, that's our tangent, so let's set that up. I know that the tangent of 25 is opposite over adjacent. Now, whatever ends up in our denominator on the right side, on that fractional side, whatever ends up in our denominator cross multiplies over. So I know that the tangent of 25 times x has to equal 100. Whatever is in the denominator crosses over and multiplies on the other side. If it happens to be your x like this one, that means that the x and the tangent of 25 get to switch places. So we get that x is 100 divided by the tangent of 25. Now please make sure that your calculator is in degree mode, or you're not going to get the right answer. If you use non-CCP kids, if you use Desmos, I think it defaults to radian measure. So be careful, hit the little gear button, get yourself in degree mode. Anyway, if we round to the nearest hundredth like they've told us, that is 214.45 feet. So that is number 16. Do we have any questions about that one? That one makes sense? Okay, so expect some of those angle of elevation and depression problems on the test. Oh, well, number 20 is exactly the same. I guess I could have just waited until number 20. Well, it isn't actually. Let's set it up. It's almost the same. Okay, let's set up number 20. It says the length of a shadow of a tree is 170 feet. So this time, our 170 is down here. And our angle of elevation is down there. What is the height of the tree? So that is the picture we would set up for this problem. It's still a tangent. The tangent of 17, because this is opposite and this is adjacent, would be x over 170. Here's the difference between those two. So maybe it's a good thing I did both. This time the 170 is what needs to cross multiply over. So this is just the tangent of 17 times 170 would equal x. Whatever's in your denominator crosses over. Now in this case we don't have anything more to do. We can just set that math up and we get to the nearest hundredths like they've asked. 51.97 feet. So obviously we're going to have a lot of, there's going to be SOHCAHTOA stuff on there, whether it's a word problem or possibly even just, I know my triangle, I'm going to give you a picture of a triangle, find all the missing stuff. Okay, so make sure that you look over your SOHCAHTOA type problems, okay? Okay, now let's scooch past some of this stuff. Please, let's look at 25. Now, for verifying trig identities, do expect that there are going to be at least one problem where you're going to have to verify a trig identity and then take a picture of the work and show me, okay? So just make sure you're showing me all the steps there. So let's take a look at C. Okay, so what I see here is that this has two different trig functions. To me, that means there's a little bit more to work with, and I can change them all into cosine. So I am thinking, and it's not wrong if you flipped it the other way, I'm going to think of let this be my answer, and then let's go from there. Well, I know that there is a Pythagorean identity which relates sines and cosines. Sine squared plus cosine squared is equal to 1. So if we solve that for sine squared is 1 minus cosine squared. Now, following our algebraic rules of simplification, this -7 by the distributive property means I'm allowed to distribute it in. So let's take that -7 and let's multiply it through. We get -7 plus 7 cosine squared. Now at this point, do you notice anything that can be combined, can be sucked together, pushed together because they're like terms? What can be pushed together because they're like terms? The 7 cosine squareds, right? Yep. They both are the same term, so 7 plus 7 is the 14 I was searching for. And I got a perfect match, I'm done. Now remember, you only manipulate one side at a time, so please make sure you're only doing that as you go through this process. So that's one where we have use of our Pythagorean. Now we're going to do D. When I see a problem like D, I think fractions give me more to do than non-fractions. So I am going to mess up the D side. Okay? Now, how do we mess it up effectively? Remember, the answer is right there on the page. The answer is secant tangent. So let's take one of the tangents, let's set it to the side, and leave the other junk there. I need a tangent by itself. Let's pull that tangent to the side. By mathematics, if that had 6, I could write that as 2 times 3. So if I have tangent squared, I can write that as tangent times tangent. So that's just a way for me to remove one piece. So then the only thing I have to do is mess this up, and I have to see, is it equal to a secant? And it's going to be, okay? I'm going to do big C over little c to that piece. Tangent is sine over cosine. Sine isn't a fraction, but anything that is a non-fraction, just put it over 1 so that it becomes a fraction. And then you get to do big C over little c. The big C stuff goes on top. We get sine of x over sine of x cosine of x. What can cancel? What can cancel? And you notice anything? The signs. Let's cancel those out. What is secant equivalent to? What is secant the same as? The flip of the? Secant is the flip of the cosine, is exactly what we were looking for. Now, I don't care if a multiplication or an addition is in the opposite order. We got the right answer. Okay? So that is how we do D. Now, if we get a chance, we'll come back to F and G, but I would like to do 26A in the last few minutes we've got. So let's do 26A. And I need you to change the instructions for me a little bit. See where it says to solve in radians the following equation using n as an integer constant. We're not doing that part. We're just going to do on the interval from 0 to 2 pi. Just add that. I don't believe I did any like that. I think I all just did between 0 and 2 pi. Okay, so you get the trig function by itself. You can even use u substitution. Remember, we did a little u substitution. And then you ask where on the unit circle does that happen. Now, it can be anything where the tangent is negative. Now, the tangent is only negative in the second and fourth quadrant. This, remember, is like radical 3 over 2 over 1/2. And the negative could either be in the top or the bottom, doesn't matter. So that is the 60 in the second quadrant. So that would be 2 pi over 3. Or the 60 in the fourth quadrant, which is 5 pi over 3. So, you got to remember your rules of equations. Let's do B. Now, I'm going to use the U technique in this one. I'm going to let U equal the cosine of x. So every place I see a cosine, I'm going to take it out, I'm going to put a U. And you can put any variable you want. And then it's just solve that equation. Now the U is already by itself on the right, so let's subtract 5 from both sides, 5 U's. -1 minus 5 is -6. Divide by -6, we get -1/2. Only once you've solved the variable do you put the trig back in. So where on the unit circle is the cosine -1/2? Now the cosine is negative over on the left. It's negative in the second and third quadrants. So we need to find our answer there. The cosine is 1/2 at the 60s. So we just need, what are the 60s over there? The 60s in the second, I think it might be the same answer up above, is 2 pi over 3. The 60s in the third, not the fourth. The third is 4 pi over 3. Okay, so that's at least some equations. I don't think we're going to get to D. I don't think we're going to do D. I don't think I did anything quite like that. So that is that. Let's stop here. Please turn this in at this time. Some of you did not turn your stuff in yesterday, which is silly. You did it with me. Turn it in. Okay? So there you go.